Yes, correct.
I would have offered you one, but this is my last working pencil.
We're ready? 1 o'clock? Where's everybody?
No idea.
Finishing their...
We should cancel class.
Oh, yeah? Yeah, we should, yes. Yep, these are the exams up here. Anybody else? They seem thick. Seems like I'm going to be busy.
I tend to cry when I did mine, so I had to keep reusing paper.
Tears of joy.
Yeah, sure.
Tears of joy.
Lagrange was so beautiful.
It isn't. Isn't Lagrange fun?
It brought a tear to my eye.
I have a friend who already did Cal 3, and he saw that I was sitting there doing some Lagrange, and was like, dude, that's the hardest part of it. And I'm like, I believe.
It's messy. All right, let's go. So we have the main takeaway from last class was, converting our coordinate system into polar, right? To make our ability to do some other geometric shapes, finding double integrals a little easier. So we can extend the ideas from the previous section that if we have two surfaces, f and g, which are traditionally functions of x and y, and we want to find the volume of the region between those two over some domain R. If that domain R is a polar region, then we convert everything over to polar, and all we have to do is subtract the double integral that we get from each one of these separately. So it's just like subtracting the top from the bottom, just like when we were in Cal 2, right? Top function, bottom function, subtract the two. Here we're just subtracting volume. So yeah, that's it. So we're going to do an example. I think we ended class, well, the last example, we proved that the area of a circle is pi r squared, right? Yeah.
Is
Okay.
the polar coordinate integrals, is that only limited to circles? Or is there other, round shapes?
Well, there can be other shapes. Now, all we talked about last class was polar rectangles, where your angle's between two constants and your radius is between two constants. So it would have to look like something like this. But you're asking, can we go more general? Yes, we're going to do an example of one. It's still going to look circular, but it's not going to be a true disk around the origin. It's going to be offset. And generally, yes, you can. Just depends on what the region looks like.
Like an oval?
Yep. We would just have to have a function that draws it in polar coordinates. Okay, this example right here. Find the volume of the solid that is below, and when I say below, I mean z-axis up is up, right? And below would mean z-axis going down, right? So I want to see if we can find the volume of the solid below x squared plus y squared plus z squared equals 1, which is a sphere, right, of radius 1. So something, find the volume of the solid that is below the sphere. So looking at the top of the sphere, down. And then we have this cone right here. Z equals the square root of x squared plus y squared. So on that cone, here's one thing you could do to kind of help yourself graph it, is think about what this looks like if y is 0. So if y is 0, we get this right here, right? If y was 0. And that, the square root of x squared, by definition, is the absolute value of x. So if I let y be 0, then z will be the absolute value of x. If x equals 0, then z will be, well, the other way around, right? The absolute value of y. Are y'all okay with the idea that that gets you the absolute value? If I take the square root of x squared, I'm saying that's the same as the absolute value of x. Are you convinced of that? Right, plug any number you want into this, right? Plug in 2, right? 2 squared, 4, square root of 4, 2, right? You get 2. That's the same thing you would get if you took the absolute value of 2. If I plug negative 2 in here, square negative 2, I get 4. And then take the square root of 4 and I get 2. So it always spits back the positive of what you put in, which is exactly what the absolute value does. So you have to now you have to know what the absolute value function looks like back from college algebra. That looks like a V, right? So in one direction it looks like a V, and then if you turn the other direction it's a V, and then everything in between is also a V. So you get the cone, right? So here's my picture. I've got a sphere, radius 1. And then the cone starts at the origin, which is the center of the sphere, and the cone goes up like this, right? And it goes forever, but I'm just going to have to draw it somewhere, right? I've got that. I'm trying to find the volume of the solid that is below the sphere and above the cone. So it's in here. It's this little piece in here. It's got a little cap to it, too. It's like a little snow cone, right? Looks like a little snow cone. Right? Do y'all see it? Below the sphere, above the cone. See, I'm not including this region here because this region over here is not above the cone. It's below the cone. So I want to know what is the volume of that. So what I'm going to do is first see that I have an F and a G, right? The F would be the top here. I guess that would be the cap of the snow cone, right? Would be our F function. And then the bottom would be the G, would be the actual cone that creates the bottom surface. So we have surface on top and a surface on bottom. Y'all good? So now what I would like to do is figure out what is the domain of this. What are the x's and y's that I'm plugging in to actually map up into these surfaces. So on the actual ground, on the xy plane, I would have my domain down here. I think I'm going to call it R. And do y'all see that R is a circle, right? Or a disk. It's everything in there as well. Thank you. So since that R on the bottom is a circle, I'm going to want to convert everything to polar coordinates, right? And also, if I want to look at my surface on top F as a surface, then I'm going to have to take this equation right here and solve it for z, right, to get it to be a function of x and y. So if I take that equation and solve it for z, I get square root of 1 minus x squared minus y squared. And then my g function is this one right here. That's already solved for z, so I can just put square root of x squared plus y squared. Top surface, bottom surface, domain, right? Let's go graph the domain over on the side. This is my R over here. It's this circle. Like that. It's a really nice polar region, right? That's a nice polar region. And so to describe this polar region, I can say my theta goes from 0 to 2 pi, right? Theta goes from 0 to 2 pi all the way around. But what about the radius? The radius is the distance from here to here, right? What does that vary between? Well, 0 and something, right? 0 and something? So my r is between 0 and, this is the question. What does it go to? What are you going to have to do to figure that out?
You said both of them equal.
Yeah, we need to know when these, this radius right here is determined by where these two hit each other, right? So I need to figure out where those two surfaces come together. So just like we have in the past, set them equal to one another would be one way we could do it, right? The important thing is for you to understand the radius is not 1, right? Because if you go out to 1, then you are going to go outside the sphere, right? It's where they hit each other is where you want to stop. So let's try and find the intersection of those two curves. I'll do it down here. So this right here, to do this, I need to find the intersection of f and g, right? So I set them equal to one another. So I set the square root of 1 minus x squared minus y squared equal to the square root of x squared plus y squared, right? Square both sides. And let's move all of our x's and y's to the right side. So we get 1 equals 2x squared plus 2y squared. And then I can just divide both sides by 2. And won't that be the equation of a circle? Right? If I divide both sides by 2. This is a circle with the radius of the square root of a half. Right? The square root of 1/2 is the radius of this circle. So this right here tells me that that outer bound, right, my outer bound for my radius is the square root of 1 over 2, which is the same as 1 over root 2, which is the same as root 2 over root 2, which you probably could have deduced already because this cone, if it's the absolute value function, this is 45 degree, right, 45 degree angle. And you can look at the sphere as being almost like a unit circle. So the x and y coordinates are root 2 over 2, root 2 over 2. I mean, you could do it that way as well, but that's just because of the nice angle here, right? This is more of the algebraic way to get to the same result. So I'm going to put that right here. I personally probably would have left it as 1 over root 2, but I'll go ahead and put root 2 over 2 here. Are there any questions on that? No? So now we set it up. I'll erase this beautiful picture. So here's what I'm trying to do. I'm trying to do the double integral over my region R, and I'm trying to take that f of xy and subtract the g of xy, and I want to do that double integral with respect to area. That's what I'm trying to do. It's the volume between the two surfaces on top of the region R. I'm going to convert to polar. So because I'm converting to polar, my double integral now is going to be first my restrictions on theta. I'm going to go theta here, so it's 0 to 2 pi. And then I'm going to do my restrictions on R, which goes from 0 to root 2 over 2. And then inside, I need my function f of xy, but I need to convert it to polar. So my f of xy, let me write it down again over here. Let me do this. I need this f of r theta minus g of r theta, and then d, sorry, what am I missing there? I'm converting to polar. I'm going to have an r here that shows up, right? And then dr d theta. I'm just giving myself another opportunity to stress that these functions of x and y must be converted to polar. And then on the next line, I'll actually write the conversion. But over here on the side, I'm going to write down what is f of r theta. Well, f of x, I don't need this. F of xy was the square root of 1 minus x squared minus y squared. Any ideas on what to do with that? To get it to polar?
X equals X.
What do we replace x with in polar? R cosine theta, and we replace that with r sine theta, right? Now, I'm not going to do that because I see something better. I showed you all this in class last time. If I factor negative out of the second two terms, then x squared plus y squared with the polar conversion is just r squared. So you would get that if you actually plugged in r cosine theta, r sine theta, but then you'd have to do more work. So I'm just going to go straight now to, this is, well, let me leave it like that. And then down here, now when I'm converting that to polar, it becomes square root of 1 minus r squared. Right? That's what f is converted over to polar. Let's try and squeeze g in right here. G of xy was square root of x squared plus y squared, but we're going to convert that to polar, so we want in terms of r and theta, and that's just going to be, it's just going to be r. Actually, the square root of r squared, which I said was the absolute value of r. However, r is always positive here, isn't it? So I don't need the absolute value. I can just put r, because it's understood that the r is never going to be negative here. So that's just r. Come on. R. Is that all right? All right, let's go in here, and then we'll set it up and almost be done. Integral 0 to root 2 over 2. And now f of r theta, which is the square root of 1 minus r squared, and then subtract from that g of r, which is just r, and then don't forget, multiply that by r, and then dr d theta. So that is the integral. That's the double integral that will give us the volume below the sphere of radius 1 and above that cone over, on top of that region. Now, I'm not going to go through the rest of this because the rest of this is just integration, but you would want to distribute the r through here, right? Put an r in front here, and you'd make that r squared. And then you could do these separately, right? When you integrate, we integrate with respect to r first. The first one is a basic u sub, right? You see the 1 minus r squared is u, and then du is out here. You're kind of off by a constant, but you could take care of that. And then this one is just 1/3 r cubed. Plug in, right? Is it all right? Just leave it to you? Everyone good with that? So dot, dot, dot. Okay. All right. Next one. Or next idea, I should say. So let me motivate this with a reminder of how we did this before. Before we went to polar coordinates, we were just working strictly in Cartesian, right? And with Cartesian, we had 3 different regions we looked at. We had the first region that we ever saw, which was just a rectangle, right? The region on the ground was a rectangle. So we had this right here, where our x was between 2 constants, y was between 2 constants, right? And then from there we moved to a type 1, right? Type 1, where you had your x's between 2 constants, but your y's were between 2 functions of x. And then we had type 2, where your y's were between 2 constants, and your x's were between 2 functions of y, right? That's what we looked at. Rectangle, type 1, type 2. Well, now we went to polar, right? And when we looked at polar, we said the similar region in terms of polar, connecting the same idea here is that we would have some sort of shape like this, right? This polar rectangle where our r was bounded between 2 constants and our theta was between alpha and beta, 2 constants, right? So alpha to beta, and then a to b was the 2 radius. That's our polar rectangle. So what do you think is next?
bounded between variables.
Yeah, like some sort of type 1 region in polar, where one of these variables is between two constants and the other is a function of that other variable, right? So like here, the x is between two constants, and our y is between two functions of x, right? I think we used like f1 of x and then f2 of x, something like that. So one of our variables is still between two constants, the other one's between two functions of that variable. So here with polar, we should be looking at a region where, let's start with the type 1, where the theta is between two constants and the r is between two functions of theta. Let me show you what that looks like. Ignore the keyboard. Not sure why that popped up on there, but I haven't removed it. It's been there for years. So look at that region. This region right here, we have our angle varies between alpha and beta. So our angle stuck between two constants, theta, stuck between two constants, alpha and beta. And our radius actually depends on where our angle is. So if you give me a certain angle, this radius is some function h1 of that theta. And then if you want to know how far to go out here, that's some other function h2 of theta. And this would be like a similar type 1 Cartesian, but this is like a type 1 in polar. We are only going to look at this case with polar. We're not going to do it the other way around. We're not going to fix the radius between two constants and vary the angle, right? We're only going to do this scenario. All right, yes?
Is it possible to do that?
Yes.
Okay.
Yes.
We're just not gonna.
We're just not going to, yeah. You could say like similarly, now the regions look different. That's the reason. The regions look kind of weird. All right, before we do an example, let's do an example. Like I've never even shown you what a function of theta looks like in polar, right? So let's just do an example of a polar function. So we're kind of stepping away, taking a quick time out here. Let's see if we can sketch this. I want us to sketch I'll call it h of theta equals, let's just say 2 cosine theta. There. The important thing to remember here, we are in polar coordinates right now, right? We are in polar coordinates. So this is the angle we're plugging in, and this side right here, h of theta, gives us the radius, right? It gives us how far to walk out. So I'm going to do this using a good old-fashioned t-table. Here's theta, here's what the radius is. Let me start at an angle of 0. So if I want to look at my xy plane, normally xy, now we're looking r and theta. When I say my angle is 0, what I mean is I'm standing here at the origin and I'm looking out at the angle of 0. So I'm looking out that way, and I need directions on how far to walk out. So what I do is I plug 0 in here. Cosine of 0 is 1. 2 times 1 is 2, right? So that means I'm going to go and I'm going to walk out 2 units. So here's 1, here's 2, and I drop a dot right there, okay? What you don't want to do is look at, like, this is like an ordered pair, 0, 2. This is not xy, right? This is not xy. This is what? Sorry, we do it the other way around. R theta. 2, 0, right? R theta. It's not a Cartesian. I'm not giving you a Cartesian point. I'm giving you the polar point. All right, what would be another good angle that you would be able to figure out pretty quickly?
90 degrees.
90, pi over 2. I'll leave a space because I'm going to do pi over 4 also. Pi over 2. So that means I'm going to aim, pi over 2 straight up, and now I need to know how far to walk out. So if I plug pi over 2 in here, cosine of pi over 2 is 0, right? So 0. So that means I turn 90 degrees, and I just don't go anywhere. I just drop a dot right there. There. Okay? Again, if you look at this as a point, 0 pi over 2, in Cartesian, that would be up here, right? But we're not in Cartesian, we're in polar. So that's that point. Let me go back to pi over 4. If I plug in pi over 4 here, so I'm aimed, pi over 4 is right there, 45 degrees. And now how far do we walk out? Well, plug in pi over 4, we get root 2 over 2, then times 2, you just get square root of 2. Square root of 2 is approximately 1.414. So I'm going to walk out not quite, like here's 1, right? I'm going to go to 1.4, about right there, but I'm aimed this way, so I don't know, it's somewhere around right in here. And we got to keep doing this to get more points to see what this actually draws, right? We have to continue to. So let me see. How about we go a negative angle? There's nothing wrong with aiming a negative angle. How about negative pi over 4? So aim down 45 degrees. What does that change? Cosine of negative pi over 4 would be, isn't that the same answer? It's the same answer, right? So you still get the square root of 2. So that means if I aim this far, right, there, I walk out square root of 2 over 2. So I'm right here. Let's see, where else do I want to, how about negative pi over 2? So if I go and I aim like this, it's going to be back at 0 again, right? Because cosine of negative pi over 2 is 0. What is this drawing, right? I need more points. Maybe I do like pi over 8, right? Do some smaller angles in here, right, to figure out. So Desmos will do this for you. Anyone know how to type in a polar onto Desmos?
You have to change the settings.
Don't think you need to change the settings. I haven't done this in a while. So I believe all you do is just type in r equals and then cosine, and then I think you just type theta. There you go. So Desmos knows we're talking about polar because I'm using r and theta instead of x and y. So it knows it. It assumes that's what I want. So what did it just draw? Oh, I forgot the 2. Yeah, I apologize. I forgot the 2. That changes. How does that change things? Oh, we'll just made it bigger. There we go, right? We just made it bigger, changed the radius. But that's just like an offset circle, isn't it? That's just like a circle. Well, at least it appears to just be a circle. So what's happening is that, you plug in, you get here, and then if we were to plug in more points, we'd start filling in these points, and then we go, comes around, right? Here, let's do this angle. We haven't tried this one. How about 3 pi over 4? This is a cool one. So that means I'm aiming in this direction, right? Okay, cosine of 3 pi over 4 is negative root 2 over 2. So this becomes 2 times negative root 2 over 2. The 2's cancel and you get what? Just negative root 2? What does that mean? I'm aiming in this direction and I'm supposed to walk out how far? Negative, yeah, so I'm moonwalking backwards to this point again, you see? So even if I do more angles, like let's do pi, right? If we do pi, where are we? Well, cosine of pi is negative 1 times 2. You get negative 2. So if we're aimed out at pi, we're going to go backwards to 2. And as I keep going around, right, I just keep dropping these points just over here, and I just keep drawing the circle over and over and over. Interesting, huh? Okay. While we're here and I've got this on the board, can somebody give me the equation of that circle in polar coordinates? I mean, sorry, in polar, sorry. There's the equation of the circle. The equation of that in Cartesian. What's the radius of that circle? 1, so it's equal 1, right? And then, so you have something squared plus something squared. It's x minus h, y minus k. This is a generic formula for a circle, where h and k are your center. So what would it be? X minus 1 and then y minus 0, right? That's what we're saying is that that Cartesian equation is equivalent to that right there, right? You could say, if you could get rid of the h of theta, you could just call this r. We could say that that polar equation is equivalent to that Cartesian equation. Yeah? So I'm going to show you one more thing. It's pretty cool. Now I'm going to need it too for the next example. So this is all leading us to the next example. I'm going to write that equation down. Right? That's the Cartesian equation of that circle. Let's say somebody gave me that, and I wanted to convert that to polar. Right? How do I get from here to here? Well, all we do is this. Let's just expand this out.
Shouldn't that be equals 1?
Yes, thank you. That's 1. Thank you. Expand, right? That equals 1. Now, anyone see anything?
Group that x squared, y squared, and make it into r squared.
Yeah, these two together added, right? X squared plus y squared is r squared. So I can replace that with r squared. Agreed? I could if I wanted to. So I have, let me get this off the screen. So I have, this turns into r squared. That's those two right there. And then minus 2 times, now x going to polar gets converted to what? R cosine theta, right? R cosine theta. So I just put r cosine theta there. And then I had plus 1 and equals 1. And the ones will just go away. And that gives you r squared minus 2r cosine theta equals 0, right? And now factor an r out of each of these. And now that you've factored, set each of these factors equal to 0. So you get r equals 0, and the other one is r minus 2 cosine theta equals 0, right? And if this one, if you move the 2 cosine theta to the other side, you get the equation, don't you? There's the equation. This, r equals 0, is just the origin point, right? That's all it is. If I say, hey, r is 0, then you're talking about the origin. It's a point where the radius, we walk out, it's 0. Okay, I'm done with that example. But I want to show you just 2 more things, okay? So if we're in polar, okay, if we're in polar and I ask you to sketch this, what are you going to draw? Circle radius 5? That's just saying your radius is always 5, right? Do you see theta in there at all?